All right, let's talk about power electronics. If you've spent any time in this world, you've definitely run into the classic converters, right? The bucks, the flybacks, all the workhorses. But in those traditional designs, the switches, the little electronic components doing all the work, they have to turn on and off while staring down a ton of voltage and current at the same time. We call this hard switching. It's basically the brute force method, and boy, does it create a lot of waste. So today, we're diving into something much, much smarter. A really elegant technique called resonant converters and the art of soft switching. This is the secret sauce that lets engineers crank up the frequency, shrink down the size, and get these incredible efficiencies we see in all our modern gadgets. And you've probably noticed this yourself, right? I mean, have you ever really stopped and wondered why the power brick for your brand new laptop is like a third of the size of that clunker you had a decade ago? Or how your phone charger can pump out so much power from a cube that's barely bigger than your thumb? Well, it's not magic, it's just some seriously brilliant engineering, and it's at the very heart of what we're going to break down today. Okay, so here's our game plan. We're going to start by really digging into the core issue, what we call the hard switching problem. Then we'll look at two fantastic solutions to that problem. First up is zero current switching, or ZCS, and then we'll check out its cousin, zero voltage switching, or ZVS. After we've got the theory down, we'll see how it all comes together as we build a series resonant converter. And to wrap it all up, we'll touch on some of the more advanced designs and the cool analytical tools you need to really make them sing. So, let's start at the beginning. We need to understand the fundamental headache that every single power electronics engineer has to deal with. It's this problem of just forcing things to work, which creates heat and wastes energy. And it happens in a split second, millions and millions of times over. This slide really lays it all out, the problem and the solution. On the left, you've got hard switching. The best way to think about this is like trying to slam a really heavy door shut while a hurricane is blowing against it. You can probably do it, but it's going to take a massive amount of effort, it's going to make a huge, loud bang, and you're going to put a ton of stress on that door and its hinges. Well, in an electronic circuit, that's exactly what happens when a switch has to turn on or off, when there's a bunch of voltage across it and a bunch of current trying to flow through it. The power lost in that tiny instant, which is just voltage times current, gets turned directly into useless, damaging heat. This obviously kills your efficiency, but it also really beats up your components and limits how fast you can do that switching. Now, look at the right side. That's soft switching. This is like waiting for that hurricane to die down to a gentle breeze before you casually close the door. By cleverly manipulating the circuit to make sure either the voltage or the current is zero at the exact moment of switching, we basically get rid of that power loss. And this is the game changer. With less heat to deal with, we can jack up the switching frequency. I'm talking from tens of kilohertz way up into the megahertz range. And a higher frequency means we can use way smaller transformers, inductors, and capacitors. That, right there, is the secret to those tiny, powerful chargers. So how do we actually do this? How do we get that perfect timing? Well, let's meet the first hero of our story, zero current switching, or ZCS. This technique is all about precisely shaping the flow of current to create a perfect little window of opportunity for us to make our move. So how does it work? Well, the key to zero current switching is to take a normal converter and add a couple of special ingredients. We very strategically add a small inductor, which we'll call LR, in series with our main switch, and then a small capacitor, CR. Now, you might look at that and think, oh, it's just another filter. But it's not. Their job is way more active than that. Together, these two parts form what we call a resonant tank, and their entire purpose in life is to grab hold of the current waveform and force it to dance to their tune, to make it oscillate in a very specific way. Think of them as the choreographers of the circuit. Okay, let's walk through this dance step by step. In step 1, the main switch closes. At first, everything looks normal. The current starts to rise in a straight, predictable line, just like it would in any old hard-switched circuit. But then, in step 2, the magic happens. Our little resonant tank circuit wakes up and takes over. Energy starts to slosh back and forth between our new inductor and capacitor. Suddenly, the current isn't a straight line anymore. It's this beautiful, smooth, sinusoidal wave. And here's the really cool part. As we get to step 3, because it's an oscillation, after the current hits its peak, it naturally just swings right back down on its own, heading straight for zero. The whole time, our control circuit is just sitting there, watching and waiting for that exact moment. And that brings us to the magic moment of ZCS, which is our step 4. The controller sees that the oscillating current has just hit zero. And at that perfect instant, it tells the switch, okay, open up. Now think about that basic power equation. Power equals voltage times current. If the current I is 0 when you flick the switch, well, it doesn't matter how high the voltage is. 0 times anything is 0. The switching loss is completely gone. It's a perfectly clean, totally lossless transition, and it's all thanks to the natural physics of that resonant circuit we designed. So how do we actually control this whole process? Well, it all boils down to two simple but really powerful numbers. The first is the resonant frequency. This basically sets the natural rhythm of the dance between our inductor and capacitor. The second is the characteristic impedance, which defines how high the peak of that current wave is going to get. As an engineer, by just carefully picking the values for that inductor and capacitor, you can perfectly tune the shape and timing of this current wave to do exactly what you want it to do. These two little equations are the entire rulebook for the dance. Okay, so ZCS is a fantastic tool for getting rid of those turn-off losses, but that's only half the story, right? There are also turn-on losses to worry about. And for that, we've got another trick up our sleeve, a complementary technique called zero voltage switching, or ZVS. And in a lot of modern designs, this one is actually even more useful. Now, the process for ZVS is a little different. First off, the setup changes. As you see in step 1, instead of a series inductor, the star of the show this time is a capacitor that we place directly in parallel with our switch, right across its terminals. Then, in step 2, while the switch is open, the voltage on this capacitor starts to resonate with other inductors in the circuit. And just like the current did in ZCS, the voltage starts to form a nice, smooth sine wave. Then, in step 3, after hitting its peak, that voltage naturally swings all the way back down towards 0. And just like before, our control circuit is just patiently waiting for that perfect moment. And that, of course, brings us to the magic moment for ZVS, our final step. The instant the voltage across that switch hits 0, the controller says go and closes the switch. Let's go back to our power loss equation one more time. Power equals voltage times current. Well, this time, if the voltage, V, is 0 at the moment you switch, then the turn-on loss is 0. Boom! Another perfectly soft, completely lossless transition. This time, we just did it by controlling voltage instead of current. So you might be wondering, why would an engineer pick ZVS over ZCS? This quote right here gives us the biggest reason. Modern switches, especially the super common ones called MOSFETs, have this tiny, unavoidable little bit of capacitance built right into them. In a hard switching design, every single time that switch turns on, the first thing you have to do is waste a bunch of energy just to discharge that little capacitor. It's like having to empty a tiny bucket of water every time you want to use it. It's a small loss, but it happens millions of times a second. ZVS totally solves this problem. By making sure the voltage is already 0 before the switch turns on, that little internal capacitor is already empty. There's no energy to waste. At super high frequencies, this is a massive win, preventing a ton of waste heat. Okay, so we've pretty much mastered the idea of the resonance switch, with both ZCS and ZVS under our belt. Now it's time to move on from these theoretical building blocks and put them together to make a complete practical circuit, the series resonant DC to DC converter. This is where we see the real power of this whole technique. So how do we actually build one of these things? Well, it starts with an inverter, usually a half bridge or a full bridge of switches. Its job is to take our DC input and chop it up into a high-frequency AC square wave. Then we feed that square wave into our resonant tank, which is usually an inductor, a capacitor, and the load itself, all in series. This tank circuit is really the heart and soul of the converter. The AC voltage that develops across that tank then gets rectified back into a nice, smooth DC voltage for our output. Now, here's the really important part about control. We don't use the normal pulse width modulation, or PWM, that you see everywhere else. Instead, we control the output voltage by actually changing the switching frequency. And the goal, almost always, is to run our inverter at a frequency that's just a little bit above the natural resonant frequency of the tank. Why? Because when you do that, the tank circuit looks inductive to the inverter. And what that means is that the current naturally lags behind the voltage, which creates the absolute perfect conditions for the inverter switches to achieve zero voltage switching all on their own. It's really clever. But this brings up a really interesting puzzle for designers. We're pumping this sharp, jagged square wave into our resonant tank. The problem is all of our standard AC circuit analysis tools, phasers, impedance calculations, all that good stuff, they were all designed to work with clean, perfect sine waves. So how on earth are we supposed to figure out how this circuit is going to behave when the input waveform doesn't match our tools? The solution is this incredibly cool mathematical shortcut called the fundamental approximation. So here's the big idea. A perfect square wave isn't really just one frequency. It's actually made up of a main primary sine wave, we call that the fundamental, plus a whole bunch of smaller, higher frequency sine waves called harmonics. The best analogy is a musical chord. You play a C chord, you hear the main C note, but there are also all these other quieter overtones that give it its rich sound. What we do is take advantage of the fact that our resonant tank is also a pretty good filter. It naturally tends to block all those high-frequency harmonics, and it really only lets that main fundamental sine wave pass through easily. So for our analysis, we can just pretend those other harmonics don't even exist and analyze the whole circuit as if we were feeding it a pure sine wave from the start. And this is where that abstract math gives us a real concrete tool for design. Using a technique from signal processing called Fourier analysis, we can mathematically break down our square wave and figure out the exact amplitude of that main fundamental sine wave that's hiding inside. And the answer is this beautifully simple formula. 4 times the DC input voltage, all divided by pi. And just like that, our messy square wave problem becomes a simple AC circuit problem. We have a known sinusoidal input voltage, and now we can use all of our standard tools to predict exactly what the converter is going to do. It's amazing. Now, the series resonant converter is incredibly powerful and efficient, but it's not perfect. Like any good piece of engineering, it has its trade-offs. So for this last part, let's explore its single biggest weakness and look at the advanced designs that were invented to fix it. So just take a second to think about this. We've designed this really efficient converter, but its behavior totally depends on the load being part of that resonance circuit. So what do you think would happen if you just unplugged the load? What is the critical flaw of this design? And here's the answer, laid out right here in this table. The pure series converter, the one we've been talking about, is fantastic at full load, but its major flaw is that it can't regulate its output voltage if there's no load attached. The voltage will just shoot up. So to solve that, engineers developed the parallel converter. It has great regulation even with no load, but the trade-off is that you get these high currents that are just constantly sloshing around inside the resonant tank, even when no power is going out. This wastes energy and makes it less efficient overall. And that, of course, leads us to the ultimate solution, the LCC, or series parallel topology. This design really combines the best of both. It has components in series to get that high efficiency, and it has components in parallel to get good no-load regulation. The only real downside is that it's more complex and has more parts, but for really high-performance designs, it is often the perfect choice. And finally, analyzing the steady-state performance is one thing, but designing a stable, responsive feedback loop for these super complex, frequency-controlled systems, that is a whole other level of challenge. The simple methods just don't work. To really model the dynamics and make sure the converter is stable under all conditions, engineers have to pull out the big guns, advanced mathematical techniques like state-space averaging. It's a way to create an average model of the converter's behavior, linearize it, and then apply all the classic control theory tools to design a really robust feedback system. So there you have it. We went all the way from the basic problem of hard switching through the really elegant solutions of ZCS and ZVS, and all the way to building, analyzing, and even improving complete resonant converters. By harnessing the power of resonance, we can switch faster, make our components way smaller, and hit efficiencies that people used to think were impossible. The big question now is, what should we explore next? Hey, if you enjoyed this deep dive on resonant converters and you want to see more explainers like this, please do me a quick favor and hit that like button and subscribe to the channel. Honestly, it's the best way to support what we're doing here, and it tells us that we should keep making more of these. We really want to build this channel around the topics that you are most curious about. So please, drop a comment below and tell us where you think we should go next. Are you interested in a really practical hands-on tutorial for designing ZVS snubbers to protect your switches? Or are you ready to go all in on the math and do a proper deep dive into state-space averaging for control design? Or maybe something else entirely? Let us know what would be most valuable for you. Thank you so much for watching, and we'll see you in the next explainer.